Welcome back, students. I am Sudipto, Assistant Professor of Physics, SAIST, and in today's class we are going to establish the expression for Compton shift in wavelength for a photon that is scattered from a free electron at a scattering angle phi. Okay, so the diagram is already given. Here, the purple circle, as you can see in your screen, it is a free electron at rest. So it is a free electron. So it is a free electron. From the left we have an incident photon that is approaching to this free electron. Okay. And suppose the energy of this incident photon, that is E equals to h according to Planck's equation, where E is the energy of incident photon, h is Planck's constant, and mu is the frequency of this incident photon. Okay. So what will be the consequent momentum? The momentum of this incident photon will be h nu by c. So it is the expression for momentum of incident photon. Okay. So this incident photon will elastically collide with this electron which is initially at rest. Elastic collision means the total energy and total momentum before and after collision will remain constant. Okay. So this incident photon and this electron at rest will collide together via elastic collision. After the collision is fulfilled, this incoming photon will hand over some of its energy to this electron at rest, and thereby the photon will be scattered away at an angle phi with some lower energy compared to the energy of this incident photon. So what will be the energy of this scattered photon? The energy of scattered photon, I assume that E prime, that is equals to h nu prime. It also can be written as hc by lambda prime. As we all know that frequency means the ratio of velocity of light to the wavelength of light. So I can also write the energy expression in terms of wavelength, that is hc by lambda prime. Similarly, I can also write the energy of this incident photon in terms of wavelength, that is hc by lambda. Okay, now what about the energy of this electron? Initially, before the collision has taken place, the energy of this electron was nothing but rest mass energy. As we all know that initially this electron which is at rest, so that means it do not have any motion. Thereby, it do not have initially kinetic energy. So all the energy in its position of rest will be simply rest mass energy. So initially this electron has rest mass energy, that is equals to m0 c square. This is the expression for rest mass energy. What is m0? m0 or m0 is the rest mass of this electron, and c is the velocity of light in free space. So m0 c square represents the rest mass energy of electron. After the collision has fulfilled, or after the collision has occurred, some amount of energy of photon is to be transferred to this electron. So what will be the net energy or total energy after collision of the electron? After collision, the total energy of this electron, I am writing it as E double prime, will be simply, initially it has m0 c square amount of rest mass energy, so it will remain same, plus some amount of energy has already transferred from this photon to this electron. Now what is the energy that is transferred? Look carefully. What is the incident energy of this photon? This is h nu. What amount of energy the scattered photon possesses? It is h nu prime. Then what amount of energy has already handed over to this electron? The amount of energy has already transferred to this electron by the collision will be the difference between these two energies, that is h nu minus h nu prime. So the amount of energy increment in this electron is h nu minus h nu prime. This amount of energy that is gained by the electron from this incident photon will be completely converted into kinetic energy of this electron, and thereby the electron will be recoiled at a particular angle theta with this horizontal axis. I am taking it as x-axis. Okay. So this is the total momentum. So this is the total energy of the electron, that of the recoil electron. Now, our main goal is to establish the expression for Compton shift, or the difference between the wavelengths of incident photon and scattered photon. Okay. Now, for that purpose, if I want to apply conservation law of momentum, then what I can write? From conservation law, or I can write it as from momentum conservation, conservation, what we can write? Look carefully. We know that momentum is a vector quantity. That means it has both components along x-axis and y-axis. That means it has both components along horizontal axis and vertical axis. So we have to deal both of them together. Okay. Now, if I talk about the component of momentum along horizontal axis, then what is the momentum of this incident photon? The momentum of this incident photon is h nu by c. It is along horizontal direction. Okay. So initially the momentum of this photon is h nu by c. And what is the momentum of this electron? Initially, as I have already told you that initially this electron is at rest. So that means it do not have any kind of velocity, thereby it do not has any kind of momentum. So on the left hand side, I have the total momentum along x-axis before collision. That means before collision, that means the momentum of this incident photon, that is h nu by c, plus what is the momentum initially before collision of this electron? 0, because it is at rest, equals to after collision. Since we are talking about the momentum components along horizontal axis, so we have to split the momentum of this scattered photon along x direction and y direction. So what will be the momentum of this scattered photon? Say its momentum is p prime, that is h nu prime by c. Okay, and this amount of momentum is making an angle phi with horizontal axis. Okay, so the component along horizontal axis of that momentum p prime will be p prime cos phi. Okay, so it will be simply p prime cos phi. Now p prime means h nu prime by c. So the momentum of scattered photon along x-axis is h nu prime by c cos phi, plus we have the recoil electron that is making an angle theta with the horizontal axis. So what will be the total momentum of this electron along horizontal direction? It will be, say its momentum is p. Say its momentum is p. Then its component along horizontal direction will be p cos theta. So this is the momentum conservation equation for both photon and electron along horizontal direction. We are writing this equation as equation number 1. Okay. Now we have to deal the same but for vertical axis or vertical direction. See, the photon is moving along horizontal direction. It is not moving along vertical direction. So there will be no initial component of momentum along vertical direction. So that is why the vertical component of momentum of photon before collision is 0 plus, since the electron was initially at rest, so its momentum is also 0. So that is why the left hand side of the momentum conservation equation along vertical direction is 0. Now after the collision, as you can see, this p prime amount of momentum of this scattered photon is making an angle phi with the horizontal direction. So we can also split it into a vertical component. Okay, so what will be its vertical component along positive y direction? It will be h nu prime by c sin phi. Okay, so this is the momentum of scattered photon and its component along y direction or along vertical direction will be h nu prime by c sin phi. Okay, now what about the vertical component of this recoiled electron? Now the vertical component of this recoiled electron, obviously it is along this direction, that means along negative y direction. So that is why I have taken it as negative of p sin theta. Since the vertical component of recoiled electron is along negative y-axis, that is along downward direction. So that is why I have taken this negative sign. Okay, so this is the energy, so this is the momentum conservation equation along vertical direction of this whole system. Okay, so I am writing it as equation number 2. Now from equation number 1 and equation number 2, we can keep this p cos theta and p sin theta in left hand side and keeping rest of the term in the right hand side. Okay, so from equation number 1, if I take p cos theta in a particular side and keeping the rest of the term in the other side, so we get p cos theta, that is equals to h nu by c minus h nu prime by c cos phi. Clear? So this is my equation number 3. This is equation number 3. Now, what we can write from equation number 2? From equation number 2, we can write as, keeping p sin theta in left hand side, we can write h nu prime by c, we can write h nu prime by c sin phi. This is equation number 4. Clear? So thereby we have made two new equations, equation number 3 and equation number 4. Okay, now we have to square and sum equation number 3 and 4. So squaring and adding equation number 3 and 4, we get, what do we get? On the left hand side we have p cos theta whole square plus p sin theta whole square. Clear? And on the right hand side we have these two terms. The first term is h nu by c minus h nu prime by c cos phi whole square plus this term h nu prime by c sin phi whole square. Okay, now if we simplify these two terms, we get p square, because we know that cos square theta plus sin square theta, it is equals to 1. and in the right hand side we have h nu by c whole square minus 2h square nu prime by c square cos phi plus h nu prime by c whole square cos square phi plus h nu prime by c whole square sin square. Now, the last two terms we have the same quantity in front of this cos and sin terms, that is h nu prime by c. So if we take h nu prime by c whole square common, we get cos square phi plus sin square phi, that is equals to 1. So this results p square equals to h nu by c whole square minus 2h square nu prime by c square cos phi plus h nu prime by c whole square. Now, if we multiply both sides by c square, then this results p square c square equals to h nu whole square plus h nu prime whole square minus 2h square nu prime cos phi. There, so this is my equation number 5. So we have an expression for p square c square in terms of frequency and scattering angle phi via using momentum conservation equation. Now we need to apply energy conservation equation. So energy conservation equation means the energy from energy conservation equation from energy conservation equation, what do we get? We get that the total relativistic energy of the recoiled electron that is E. It is the total energy, or total relativistic energy of recoiled electron, that is equals to root under p square c square plus m0 square c to the power 4, where p is the momentum of the electron, c is velocity of light as I have already said, and m0 is the rest mass of the electron. Okay, so this is our equation number 6. Again, from the diagram, what do we get? So if I scroll down the total screen, we get the total energy of the recoiled electron, that is E double prime. As you can see, it is the sum of the rest mass energy of the electron plus the amount of energy that is gained by the electron from the photon via elastic collision. That is m0 c square plus h nu minus h nu prime. So it is also the total relativistic energy. Again, the total energy of electron, that is E double prime, it is equals to m0 c square plus h nu minus h nu. This is our equation number 7. Now, what does equation number 6 and equation number 7 tells us? Equation number 6 tells us it is the total energy of the repel electron. Electron number 7 also tells us that it also represents the total energy of the recoil electron. So that means they both are same because they both represents the energy of recoil electron. Okay. So if I equate equation 6 and equation 7, then we get from equation 6 and equation 7 we get, because they both are same, they both are energies of recoil electron, so I can easily equate them. Okay. So we get, on the left hand side I have to write this term, root under p square c square plus m0 square c to the power 4. And on the right hand side I have to write this term. This is m0 c square plus h nu minus h nu prime. If I square both sides, what do we get? If I square both sides, in order to remove this square root term, okay, then we get on the left hand side we have p square c square plus m0 square c to the power 4. Okay, and on the right hand side we have m0 c square whole square plus 2 into m0 c square h nu minus h nu prime plus h nu minus h nu prime whole square. Okay, so we get p square c square plus m0 square c to the power 4 equals to, this gives us m0 square c to the power 4 plus 2 m0 c square h nu minus 2 m0 c square h nu prime, plus I have to expand this term, so this gives us h nu whole square minus 2 h square nu prime plus h nu prime whole square. This is our equation number 8, I guess. So this is our equation number 8. Okay. Now look carefully that on the left hand side we have p square c square plus m0 square c to the power 4. Okay. So these two terms easily cancel out. So the only term that remains on the left hand side is p square c square. And if you remember that we already have established the expression for p square c square, that is this term. So I can easily substitute from equation number 5 the expression for p square c square. Okay. So it gives us, from equation number 5 we have p square c square. It can also be written as h nu whole square plus h nu prime whole square minus that is minus h square nu prime cos phi minus 2 h square nu prime cos phi. And on the right hand side we have 2 m0 c square h nu minus 2 m0 c square h nu prime plus h nu prime whole square minus 2 h square nu prime plus h nu prime whole square. Okay. Now this h nu prime whole square, this h nu prime whole square and h nu whole square, and this h nu whole square, h nu prime whole square, these two cancels out from both sides. Okay. So these two cancels out, and the term that remains is minus 2 h square nu prime cos phi, that is equals to 2 m0 c square h nu minus nu prime minus 2h square nu nu prime. So if I keep this term in the left hand side, so it gives us 2h square nu nu prime. Within bracket we have 1 minus cos phi, and we have on the right hand side 2m0 c squared h nu minus nu prime. Okay, so these two and these two cancels out, this h and this h also cancels out, and we only have that h by m0 c square. I am just rearranging all the terms from both sides. Okay, 1 minus cos phi, that is equals to nu minus nu prime divided by nu nu prime. Okay, now if I interchange both sides the terms, so we have nu minus nu prime by nu nu prime, that is equals to h by m0 c squared 1 minus cos phi. Okay, this gives us, if I split this term into two different terms, then we get 1 by nu prime minus 1 by nu, that is equals to h by m0 c squared 1 minus cos phi. Now if I multiply both sides by c, then we get c by nu prime minus c by nu, that is equals to h by m0 c 1 minus cos phi. Now look carefully, c by nu prime, we know that wavelength, it is equals to the velocity of the wave divided by its frequency, and it is also applicable for light also. Okay, so c by nu prime, it is nothing but lambda prime, that is the wavelength of scattered photon. Okay, minus what is c by nu? C by nu is nothing but the wavelength of incident photon, that is lambda. So left hand side we have the difference between the wavelengths of scattered photon and incident photon, that is lambda prime minus lambda, that is equals to h by m0 c 1 minus cos phi. So this relation, that is the difference between the wavelengths of scattered photon and incident photon, this relation is known as Compton shift. This relation is known as Compton shift. Okay, and the term that is outside of this first bracket, h by m0 c, this term is known as lambda c, which is also known as Compton wavelength. That has a numerical value 0.02426 angstrom. Okay, so thereby we have established the expression for Compton shift, as you can see in the screen. Thank you. I hope you learned pretty much about Compton shift and quantum theory. See you in the next video. Till then, keep learning. Thank you. Sad. 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 হয়ে হ্যাঁ ঠিক আছে, ওটা একটু না একটু করে বাদ দিন। এটা তো হয়ে গেল, আর একটা ভিডিও করতে